Okay, so we're going to continue from our lesson from yesterday, and we're talking about elastic potential energy, right? And our last question was we did a math problem here with this, right? Okay. What was our answer for 31? What answer did we come up with yesterday? What answer did we come up with yesterday for 31? Just a little review here. What did we come up with? What was our answer? Was it 5 joules? Is that what you come up with? Okay. Okay. That's good. Everybody got it, right? Okay, so now I'm going to move on to number 32 here. Okay, so think about us. We talked about how different size springs go on different things, right? Like you'd have a spring that goes on a garage door that pulls the garage door down or up, and then you have a slinky. You have a spring and a pin, and then you have a trampoline spring. Which one of these would you say would be the smallest spring constant? That'd be the smallest in size. Would it be a slinky or a spring and a pin? B or C? That's your only choice. Which one of those do you think would be the smallest spring constant? You remember what constant means? It's the size of the spring. Okay. Which would be the smallest? A slinky? Think about that slinky. Or a spring inside a pin. You know what that is, right? When you, matter of fact, Mr. Hughes has one right here. Look right here. There's a spring inside there. You can hear it click, actually. Okay, there's a spring inside there. Which would be smaller, this spring or a slinky? B or C? Mark your answer. Everybody got an answer?
Mm-hmm.
Was that an easy answer?
Mm-hmm.
Okay. Okay, so let's think mathematically again. Okay, so if you remember right, when we talked about kinetic energy, look at these two formulas right here. Elastic potential energy, or EPE, equals 1/2 times K, which is constant, right, times x squared. And then look over here. We did this, the very first thing we did. Kinetic energy, or KE, equals 1/2 times mass times, what's this right here? Velocity square, right? Remember that? So these two, the equation for EPA is very similar to the equation for kinetic energy. And remember that in the equation for kinetic energy, energy was directly proportional, listen to this, directly proportional to the mass, okay? And it was directly proportional to the square of the velocity. So what do you think, would this be directly proportional, do you think, if these are very similar? What would you think? Would you think they're going to be proportional? In other words, they're going to be related to each other, right? What would you say, Lily? Would they be directly proportional? We're guessing. We don't know yet, we're just guessing. What would be your best guess? Do you think they're going to be proportional?
I think, yeah. They're going to be proportional.
Okay. What do you think they're, Iris, you think they're going to be directly proportional? It's okay to be wrong. We're just making an educated guess now. What do you say there, DJ? Would they be, do you think these would be directly proportional? These are similar ways to determine the energy, right? You think they'd be directly proportional? They are here. Would they be there? They are here, so would you think they'd be here too, based on the way the problems are set up? Okay. What do you say, Daniel? What do you say there, Isaiah? You think they'd be directly proportional? Okay. Sophia, what do you think? Directly proportional or no? It's okay to be wrong, just guess.
Proportional.
Okay, so actually, guess what? EPE is directly proportional to the spring constant, just like in the kinetic energy. The comparison would be the mass, right? Spring constant, that's the size of the spring. And mass is the size in kinetic energy. And then EPE is directly proportional to the square of the distance, and distance is, you could compare it to the velocity in kinetic energy, right? how far you stretch that spring. Okay, so both are directly proportional to the square of whether it's compressed or stretched, either way. You can compress it, or you can stretch it, okay? They're directly proportional, just as it is in kinetic energy, okay? So elastic potential energy is directly proportional just as kinetic energy is, okay? Okay, so here's a question here. Okay, triple. Triple. What do you say here? Triple, would it be what? I'm gonna help you out here because you have no idea. What's triple mean? Mark your answer. What's triple mean? 3, right? You know what triple is, right? 3. Got it? Okay. Give you a little context there. Okay. Let's look right here. If it's half, what's half? What's half? What's half? Mark your answer. What's half? Show me what half is on your paper. In the spring, if the spring constant K is halved, by what factor does it? So if it's halved, what is it? You can show it two ways as far as I'm concerned. One, you type into the calculator, or you punch into the calculator. What does halved mean? If it's halved, if it's half, mark your answer. Half. Okay, and we'll talk about these here in a second. Okay, so if the distance of spring is stretched is increased by a factor of 6. Now these are proportional, so they should be the same what? So what factor is the EPA increased? Is it 6 or some other number? Mark your answer. Mark your answer. These are directly proportional. Okay, everybody got an answer? This is so easy. Right, is this easy? Because we say it's directly proportional. So if this is 6 here, what factor would the EPA increase? It's directly proportional. That means it's going to be the same. So what number are you going to put in here? Got the idea? Directly proportional means same or similar. Okay, so we're going to grade these later. Okay, I'm going to move on to conservation of energy. Okay? Woo, are you glad the math part is done? You're not? You want more math, Lily? Lily wants more math? Okay. Anybody, who else wants more math? We can do several more of these problems. What? Are you raising your hand there, young lady? Okay, so let's talk about conservation of energy. We've been talking about laws. Well, there is a law of conservation of energy. Okay, and that's what we're going to talk a little bit about. Okay, so look right here. Where are we back? We're right where we started, right? Look right here. Where did we start this with? With a roller coaster, right? And we're right back there again. So let's talk a little bit about conservation of energy. Okay, what we've looked at so far is that an object has kinetic energy, right? If the object is in motion. So anytime you hear the word kinetic energy, you automatically respond with what? Motion, right? Kinetic energy is motion. Okay, so the faster the object is going, the more kinetic energy it has. That's just a given, right? Okay, so in order for an object's kinetic energy to increase, it must get energy from somewhere. Where does it get that energy from? Where do you think where does it get it from? Where? Where does it get it from? From where? The what? Let's find out. Where to get that energy from? Let's find out. Okay, so in order for an object's kinetic energy to increase, it must take energy from its where? Stored energy. Say, here's my model right here, right? My famous dodgeball. Look here, where's it going to get where's it going to get the kinetic energy from? From the what? The stored gravitational potential energy right in here, right? And the mass is going to determine, or gravity is going to determine the kinetic energy, right? It's gonna pull it down to Earth. So where does kinetic energy get its energy from? In a nutshell, potential energy, right? Okay, it gets it from potential energy. The higher the object is, the more potential kinetic energy, right? We'll see, we'll follow along with that. So in order for an object's kinetic energy to increase, it must take its energy from stored energy, which we call potential energy. Okay, so when this happens, the potential energy that an object possesses decreases. So you got that stored energy, it's kind of like a battery. You put a battery in your phone, there's a battery in your Chromebook right there. You can't access it, but technicians can. There's a battery in there, and that's the potential energy. When you turn it on, guess what? It releases some of that potential energy, and it becomes kinetic energy. Electrical energy, right, in this case, because there's different kinds of kinetic energy. That would be non-mechanical energy. Remember, there's two kinds of kinetic energy. There's mechanical and non-mechanical. Non-mechanical would include electric. Okay, so we get our kinetic energy from our stored energy, which we call potential energy. Okay, so now stay with me here. Even though kinetic and potential energy are changing, the total energy, and it's represented by TE, a little more math, even though the kinetic and potential energy are changing, the total energy, which is represented by TE in that closed system contains, does not change. Okay, and this is a law. This is called the conservation of energy. And then you have initial total energy and you have final total energy. TE little I, TE little f, okay? So these equal each other. So that means they just loop, essentially, okay? All right, let's move on here. So when energy is conserved, that means saved, okay? It doesn't go anywhere. So when energy is conserved, no energy is added or taken away from the system, okay? No energy is added or taken away from the system. The total energy you start with is the total energy you end with. TEI, right, little I, total energy initial is equal to total energy finished. Now that sounds kind of like almost too simple, right? But that's how simple it is. It stays the same, okay? It just cycles between potential and kinetic. So in other words, energy cannot be created or destroyed. That's the law. That's a physical law. Okay. Energy cannot be created or destroyed. It can only transform from one form to another. Okay. Okay. I'm going to for you at home, I'll stop this video. And we will. You're gonna answer all those. Make sure you got those questions answered up to number. What was that last number we had? 32. Mm-hmm. Up to 32, and then if you have those answers up to number 32, I want you to submit that document to me. Turn it in. Okay. Make sure you have the answers on it. Otherwise, I can't give you a grade. So go back and look. Make sure you answered all those questions to the best of your ability. It's okay to be wrong. What science is a learning process. And make sure you have those up to 32 and then submit those to Mr. Hughes.